Welcome to the next class on biostatistics and design of experiments. We will talk more about t distribution, z distribution and also confidence interval. That means I had mentioned before, if I am collecting a sample and getting a mean and I want to find out what is the confidence interval on the population mean, I can use some equations to get that sort of information actually. So, that is what we are going to talk about in this class. Let me again recall, suppose I have a population and I have a sample. So, that means I collect a few pieces from the population and I get a mean. Now, when I take another set of pieces, I may get a different mean. If I keep on repeating, I will get large number of means. The means are a representation of the population mean, that means the means of the sample are representation of the population mean, but the standard deviation that is going to happen because the means will be distributed in a normal way, the means of the samples are going to be distributed in a normal way and there is going to be a standard deviation associated with that. So, from that standard deviation we should be able to get the overall estimate of the standard deviation. Okay. So, generally the sample mean is a usual estimator of the population mean, and if I take different samples I will get a large number of means which will have its own mean, that means mean of all the means, and it also will have a distribution, a normal distribution with its own variance. Okay. So, the standard error of the mean, we call it standard error, is the standard deviation of these sample means estimate of the population. So, how do you calculate standard error? We get the standard deviation of the sample divided by square root of n. Okay. This is called the standard error, okay, or standard error of the mean. Okay. So, this S is the sample standard deviation, n is the sample size. So, if I am taking a set of samples, I will get a mean. Now, I put it back, then again take another set of samples, I will get another mean. If I keep on repeating, I will get large number of means. Now, these means will be normally distributed, it will have its own mean, that is the mean of all these means, and it will have its own standard deviation because the whole data will be normally distributed. So, I can calculate the standard error of this mean, or it is also called standard error, okay, based on the sample standard deviation. So, S is the sample standard deviation, n is the number of samples you take and you do a square root and divide it actually. Okay, so, this is very important, standard error of the mean is very important because we use this in calculating confidence interval on whatever data we collect. Okay. We will see that as we go along. Now, let us look at a problem. Height of certain variety of pulses is normally distributed, is given a mu 14 and a sigma is 3. What is the probability in a sample of 9 plants? Suppose I take 9 plants, okay, in a random, that they will, the heights will lie between 12 and 16. Okay. What will be the statistics? So, you remember this, Z is equal to x minus mu by sigma. Now, this sigma we do not know, but we know only the standard deviation of these samples, okay, right. So, instead of sigma we need to substitute by S divided by square root of n, if you remember in the previous equation, right, S divided by square root of n. Okay. So, because we have the estimate of the standard deviation from the sample, we do not know the population, okay, right. So, we use this here and sigma is given as 3, okay, square root of 9, we have got 9 plants, okay. So, 3 by 9 square root which will be 1. So, Z is equal to 12 minus 14, okay, because we want to find out from x of 12 to x of 16. So, Z is equal to 16. So, we will get minus 2 and plus 2. So, I want to find out the area between minus 2 and plus 2. If you remember long time back we did that from the Z table, okay, this is the Z table, okay, 2 you will get it as this 0.0228, but the catch here is it estimates this region, okay. So, if I want to know this region I will subtract from 0.5 minus 0.0228. Okay. So, that is the catch here, if you remember, because the Z table gives you only the outer one tile, but this whole area is 0.5. So, if I want to know this inside portion, that will be 0.5 minus 0.0228, and then it will become 2 times, because I am interested in -2 to +2. Okay. So, I will get 0.9544. That means 95% of the time, okay, the height, if I take 9 plants, will lie between 12 to 16 actually. Okay. You understand how to solve this. So, here we use the estimate of the standard deviation based on the sample. That is why we use S divided by square root of 9. Okay. Now, again going back to the t distribution, the confidence interval of the mean. So, I take a set of samples and I get a mean, that is x bar, okay, and I get a standard deviation of that sample, okay. So, that is S divided by square root of n. If you understand this is the standard error multiplied by t. T is the t value, and it will vary depending upon whether it is 95% confidence interval or 99% confidence interval. Okay. So, generally if n is large, 95% confidence interval, t value will be 1.96. If n is large, 99% confidence will become 2.58. If you remember long time back, I did mention how this 1.96 and 2.58 can logically come. So, for very large n, if you take a normal distribution, plus or minus 2 sigma occupies approximately 95% of the area, and plus or minus 3 sigma occupies the 99% area. So, instead of 2 and 3 here, we are using 1.96 and 2.58 because we are using t distribution. As I said, it is impossible to get population. So, we can only get a sample, and from the sample we make an estimate of the population values. That is why these numbers, instead of 2 and 3, it became 1.96 and 2.58. So, if I have a small sample and I get a mean and I get a standard deviation, okay, then I can get a confidence interval for the population mean using this data by using this formula. Okay. This S by square root of n is called the standard error. T is the t value from the t table. I will show you the t table, and for large n, the t value for 95% confidence will become 1.96, and for 99% confidence it will become 2.58. And I also mentioned how you what is the logic of this 1.96 and 2.58. As I said, in a normal distribution for a 95% of the area is covered inside plus or minus 2 sigma, and 99% of the area is covered by plus or minus 3 sigma. So, instead of using 2 and 3, because it is a t distribution and sample is always much smaller than the entire population, 2 has become 1.96 and 3 has become 2.58. Okay. And that is how you use that formula. So, you have mu is equal to x bar plus or minus t d of S by square root of n. So, if n is small, there is a table called t table for corresponding degrees of freedom, where degrees of freedom is equal to n minus 1. We can get the t value, and you multiply from the standard error with the standard error, and from the x bar, that is the mean of the sample, you get the confidence interval for the population mean. In Excel there is a function called confidence. It is alpha. Alpha is the significant level. Okay. So, it can be 0.05 or 0.01. 0.05 indicates 95% confidence, and 0.01 indicates 99%. So, you have the standard deviation is the population standard deviation for the data, and size is the n actually. So, basically it gives you this side of it. So, if you know the x bar, you add and then you subtract to get the confidence interval. So, we can use the Excel function called confidence also here. Okay. There is another terminology that is called the coefficient of variation, CV, generally we call it. It is a relative standard deviation. it is a standardized measure of dispersion of a probability distribution. So, CV is given by 100 into sigma, that is the standard deviation divided by mean. So, it tells you what is the relatively the spread in the data, because you have the standard deviation in the numerator and you have the mean in the denominator. So, if CV is very large, that means my spread is very large. If CV is very small, that means my spread is very small. So, CV is a quick measure of telling how bad or how good the spread of the data is, and if I have two sets of data and I know the CVs, I can tell which data set is more spread out or which data set is more tighter and less spread out. So, that way CV is also a very useful property which we can calculate and make use of in comparing different data sets. Okay, let us look at a problem. Heartbeat of 113 students is given there, that is 2 students have 57 beats per minute, 4 students seem to have 62, 11 students seem to have 67 and so on. So, if you add up all these, it comes to 113. Okay. So, it goes right up to 117, that means 4 students have a heartbeat of 117. Now, we can get a mean for the entire data set, but that is not the population mean. We can get a confidence region for the population mean based on the sample mean, and you are supposed to calculate what is that confidence interval for the population mean for 99% data, okay, and also calculate CV. So, it is quite simple. So, what we do is we can calculate x bar from this data, then we can calculate standard deviation, that is S from this data, and I know n, and then for 113 students the degrees of freedom is 112. So, I go to the table, generally the data is large, so now for 99% t value will be 2.58. So, I multiply 2.58 multiplied by the standard deviation of this data divided by square root of n, that will be the variation in my x bar. Okay, x bar is my average. So, we can use the we use this equation, understood. So, we calculate the x bar, that is the mean of the entire data, and then we calculate the standard deviation of this data, entire data, and n is 113. Now, t is my t value which I can determine for 112 degrees of freedom, because I have 113 data. So, generally the t value here will be 2.58 because the data set is large. Okay, let us do the problem using Excel, it is not very difficult. So, first I need to, then total number is 113. Okay, now I need to find out the average mean of the entire data set. So, what do I do? 57 into 2, 62 into 4 and so on, then I add up all of them divided by 113. So, I get an average of 80.23. So, this is the average heartbeat of all the students, but if I want to get a confidence interval on this data, because this is a sample, obviously I need to calculate S. If you remember the previous equation, I need to calculate S because S is important and t will be 2.58 in this case, square root of 113, that is what is going to happen here. So, how do I calculate this? I will, this is the mean, so every time I will subtract from the mean and then I will raise square, right. You know how to calculate standard deviation, that is not very difficult. Okay, so, you get like this, the sample variance will be divided by 113, that is 1.32, and then when I take square root of that, that will be 1.15, because here I need to take square root, right. So, I am taking the variance itself and then taking the overall square root, that is what I am doing. Okay. So, I get 1.15. Now, t as I said is 2.58. So, 2.58, okay, 2.58 into 1.15, that will be plus or minus on 80. Okay. So, 2.58 into 1.1 is around 3. So, that is why the lower limit will be 80 minus approximately 3 and the upper limit will be 80 plus approximately 3, that is 83. So, the confidence interval gives you an estimate of the where the population mean will lie based on the sample mean. The sample mean is 80.2 and the sample standard error is 1.15, that is s by square root of n is called, as I mentioned here, okay, the standard error of the mean s by square root of n here. Okay. So, I multiply by 2.58 because t is given by 2.58, okay, and that is for 112 degrees of freedom for 99%. So, I use that. Now, CV is my coefficient of variation, formula is 100 into sigma divided by mu. Okay. So, the mu is 80.2, okay. So, the mu is 80.2, and then we have sigma here given here. So, we can divide by the multiply by the sigma divided by 80.2, and that will give you my what, the coefficient of variation. Okay. So, quite a simple problem, okay, we can calculate. So, this is the upper and lower limits for the heartbeat with 99% confidence, okay, based on a sample of 113 students. Understand? Okay. Okay. So, there are many statistical tests that are available which you need to use to compare two sets of data and say whether one set of data is different from another set of data or they are similar and so on actually. So, there are many tests here. Before you perform any test, we need to create the hypothesis. As I mentioned, you have the null hypothesis and the alternate hypothesis, H naught and HA, or some people use H naught and H1 and so on. So, H naught is no difference, status quo, and so on actually. HA is there is a difference, or drug A is better than drug B, or drug A is less than drug B, and so on. That is the alternate. Okay. So, that is the hypothesis. So, you create the hypothesis first, and then after that you have the data sets, you calculate the p value, okay. Then you decide on whether it is a one tail or two tail. I did talk about these tails also. So, if I am saying I am comparing two drugs and I am saying there is no difference between drugs, or alternative there is a difference between drug, then we use a two tail test. Okay. So, if I am comparing the heights of a student in class 11A with the students in height in 11B, and I am saying there is no statistical difference in their heights. So, my null hypothesis will be H, okay, H naught null hypothesis, there is no difference in the heights, HA will be there is a difference in the height. Okay. So, in such situations we are not bothered whether the height is of class A is higher or more than the height of students in the class B, or height of students in class A is less than that of the height of the students in the class B. We are not bothered about greater or less, but we are just saying they are different. Okay. In such situations we use the two tailed test, whereas if we are talking about greater or less, things like that, then we use a single tail test. Okay. So, you decide on the tail, okay. Then you decide on the p value. P value am I looking at 95% confidence interval, or I am looking at 99% confidence interval. So, 95% p will be less than 0.05, 99% p will be less than 0.01. So, I do that calculation, okay, and then yes, p is less than 0.05 or p is not different, and so on actually. Okay. So, either I will reject the null hypothesis, or I will not reject the null hypothesis. Okay. So, if there is no difference, p is less than 0.05, no, then I cannot reject the null hypothesis. Yes, p is less than 0.05, then yes, I need to reject the null hypothesis, then only I will accept the alternate hypothesis. So, initially you start with the hypothesis H naught and HA, okay, then you decide on your p value should be 95 or 99, then you decide on a tail, should it be single tail or double tail, then you calculate the p value, okay, and then you compare p value less than 0.01 or 0.05, okay. Then if it is less, then obviously you will reject the null hypothesis, so you will accept the alternate hypothesis. P value is not less than 0.05 or 0.01, so you do not reject the null hypothesis, okay. So, there is no reason for you to reject the null hypothesis. This is how any statistical analysis is carried out, and this is called the hypothesis testing. So, how do you calculate the p value? That depends upon what you are comparing. Am I comparing means between data? Am I comparing the mean of a data with some population mean? Am I comparing variation of one data set, the variation of other data set? So, you have different types of tests, t test, f test, chi-square test, so many different tests, and that is what you do here to calculate the p value, okay. So, there are many types of tests. So, for a two tail and a single tail test, for example, in a null hypothesis, suppose you are looking at sleeping pattern because of the drug, we can say there is no difference, whereas alternate could be there is a change at a alpha of 0.05, that means 95% confidence interval, okay. So, then it becomes a two tail test, there is a change, we are not saying greater change or less change, okay, but there is a change, okay. So, we use two tail both sides, but that is there is a change, that means mu which you calculate is different from mu naught. So, there is a difference, so it is a two tail test. Whereas, if you say the mu, the new sleeping pattern is greater than the old sleeping pattern, okay, mu naught could be 7 hours, so there is an increase in the sleeping pattern, okay, then it is an upper tail test, that is a single tail test, or mu is less than mu naught, that means the sleeping pattern is less than 7 hours, there is a decrease, then it is a lower tail, again it is a single tail test. So, in these two type of situation, your H naught will be mu equal to mu naught, H1 will be mu equal to greater than mu naught or mu equal to less than mu naught, depending upon whether I am looking at the drug enhancing sleeping pattern or drug reducing sleeping pattern, then it is a single tail test. Whereas, if you have H naught equal to mu is equal to mu naught, H1 is equal to, that is H alternate hypothesis is equal to mu is not equal to mu naught, then we use a two tail test. You understand, this is very important, how to zero in on the tail, should I zero in on single tail or should I zero in on two tail test, okay, that is very important when you do a statistical analysis. As I showed here, you need to decide on the tail, because most of the tables, whether it is a T table or any other Z table, the area under the curve, if it is a single tail is only one side, whereas if it is a double tail we need to consider both the sides of that area, if you remember that very clearly in our previous lectures. Okay, so, you formulate the hypothesis and then you calculate your p value based on the type of equations you use, then you decide on whether it is a single tail or a two tail test, then you decide on am I going to look at it at 95% or 99%, then you say the p you have calculated, is it less than 0.05 or it is greater than 0.05, if it is less than 0.05, okay. And if it is greater, then obviously we cannot say null hypothesis can be rejected, whereas if it is very small value we can say there is no reason for rejecting the null hypothesis, okay. Okay, so these upper tail and lower tail, let me again spend some time. So, you know the normal distribution and you know the area. So, as the outside area is more important than the inside area, okay. So, if you are talking about 95% confidence, the outside area will be 5% or 0.05. So, one side will be 0.025, other side will be again 0.025. So, for a t value of 1.96, for a two tail this area will be 0.025 and that area will be 0.025, okay. That is called a two-tailed test. Okay. So, for a two-tailed test for different alpha, as you can see, that is, this is 95%, this is 90%, this is 80%, and this is 99%, and so on actually. Okay. So, for a 95% two-tailed test, z is equal to 1.96, just like t is equal to 1.96. Okay. So, this area and this area are equal amount actually. So, it is 2.5% and 2.5%. Whereas, if you are taking a single tail test, whether it is upper tail or lower tail, you are considering only one side of the area. Okay. For upper tail, you are considering this side of the area. For lower tail, you are considering only this side of the area. Okay. Remember that. So, for a 95% confidence interval upper tail test, you have 1.6425, sorry, 1.645. Okay. So, as you can see, when upper tail 0.025, you get 1.96. If you again go back here, 0.05, 1.96, because one side 0.025, other side 0.025, together is 0.05, which is 1.96. You see this? You see this? So, for a upper tail test, your alternate hypothesis could be mu greater than mu naught, and null hypothesis is mu equal to mu naught. So, for a lower tail test, again it is the same things here, z is equal to minus 1.96 here will give you 0.025, z equal to minus 1.645 will give you 0.05. Okay. So, it is the same, but only thing is here the z the signs have changed, area is the same, but the signs have changed. So, for a lower tail test, your hypothesis could be null hypothesis could be mu equal to mu naught, and alternate is mu is equal to less than mu naught. Okay. For a alpha is equal to 0.05, if you get h naught, if z is equal to less than 1.645. So, you should get z is equal to greater or t equal to. So, z and t seem to be analogous to each other, as you can see in this particular statistical area. Okay. So, you have three types of situations. One is called the two-tailed region, that means if it is a 95%, outside area is 5%. So, you divide equally on both the sides. So, you get 2.5% and 2.5%. So, for a two-tailed test, if you look at the table for a 0.05, you get this value as 1.96 or t as 1.96. Whereas, in a single tail test, you are considering only one side of the area. If it is an upper tail, you have area on the upper side. If you have the lower tail, you have the area on the lower tail. Okay. So, for a 95% upper tail test, the z value or t value will be 1.645. For a 95% lower tail test, again the z value will be minus 1.645. And as I said, if you look at 0.025 alpha, you get 1.96, which is similar to this, because when I take 0.05, we are considering 0.025 plus 0.025 to get 0.05, and that is why this term here and this term here matches. Do you understand the entire logic here? Okay, this is how you go about doing a test of significance for any data set. So, again let me go back. So, we create the null hypothesis. Null hypothesis is there is no difference or status quo. The alternate hypothesis could be there is a statistical difference between the new data set and the old data set. Then we use a two-tailed test, because when we are saying there is a difference, we do not say whether the difference is more or less. Whereas, if the alternate hypothesis is the new data set is greater than the old data set, could be height, could be IQ, could be drug, then we use a single tail test. This is called upper tail test because greater. When we say the new data set is lower than the old data set, then we use a lower tail test, or again that is a single tail test. Okay. So, you decide on the type of test, and then you decide on what should be my p value at which I am going to study. Am I going to study at 95% confidence or 99%? So, for a 95% p is equal to 0.05. Okay. So, from that 0.05 I can get a t value or a z value. Then I calculate my t or z value based on the type of test I am going, and then I tell whether this calculated p value is much less than what is given in the table. If it is less, yes, I can reject the null hypothesis and accept the alternate hypothesis. If the p value which I calculate is not, then obviously I cannot reject the null hypothesis. The t value which I calculate is much larger than the table value, then I need to reject the null hypothesis. If the t value I calculate is much less than the table value, then I cannot reject the null hypothesis. And that is how you go about doing statistical comparison of data sets, either comparison of means or comparison of variance or comparison of ratios and so on actually. Thank you very much.